In this session, we'll discuss about interrupts. Generally, what is an interrupt? Anything which breaks the continuity is nothing but an interrupt. When we talk the same interrupts with respect to the processor, then a signal which disturbs or which breaks the continuity of execution of the processor is nothing but an interrupt. Okay, so let us see the interrupts which are present in case of 8051. Okay, so these are the things which we are going to discuss in this session, that is interrupts in 8051, programming timer interrupts, external hardware interrupts, serial communication interrupt, and then how to set the priority for those interrupts. Now this is the block which we are going to discuss now. This is the interrupt control block, which is going to receive the interrupts, that is external interrupts, and then it provides those interrupt requests to the processor. Okay, so we'll be discussing about this block. Now how the input output services are provided by the processor to the peripherals. As we know that all the peripherals along with the processor are connected to the system bus. Now if any peripheral wants the service of the processor, then it would be requesting the processor. But how the processor is going to recognize that any peripheral requires its service or not? Now that is done in two ways. One is interrupt method and the other one is polling method. Okay, an interrupt is an external or internal event that interrupts the microcontroller to inform it that a device needs its service. So in case of interrupt, it can be an external signal or it can be an internal signal which is going to disturb the processor to intimate that the device requires its service. Okay, let us see what is this polling method and then interrupt method. Now what happens in polling method? In this polling method, the processor has to monitor the status of each and every peripheral continuously. Okay, and after that it moves on to the monitor the next device until everyone is serviced. So here what it has to do is it has to monitor the status of each and every peripheral, and as soon as it recognizes that one of the peripheral requires its service, then it provides the service and then continues to monitor the next device. Okay, and it does this monitoring operation in round robin fashion. Okay, so with this polling method, what happens here is we are wasting the efficient use or efficient time of the processor. So in order to overcome this drawback, now in most of the computers, interrupt method is used. Let us see what is an interrupt method. Whenever any device needs its service, the device notifies the microcontroller by sending it an interrupt signal. Okay, upon receiving an interrupt signal, the microcontroller interrupts whatever it is doing and serves the device. So here the processor would be continuing its operation until it receives any signal from the device. So here it would be continuing its operation. As soon as it receives any signal from the devices, then it will respond to those devices. Okay, so the program which is associated with the interrupt is called as interrupt service routine or interrupt handler. Okay, so here for example, assume that processor is doing a task, and during the period of that time, assuming that one interrupt is generated, now the processor will respond to the interrupt by executing the interrupt handler, okay, related to that particular interrupt. Okay, providing a service here is nothing but executing the ISR which is related to that particular interrupt. Okay, so in this interrupt method, so as the processor would be doing its own task without monitoring the status of each and every device, therefore the time or the efficient time of the processor is used in a good way. Now what is the advantage of interrupts? As I told you that the microcontroller can serve many devices. Each device can get serviced based on the priority assigned to it. So here if multiple devices are generating the interrupt at the same time, then the processor is going to provide its service based on the priority which is assigned to those interrupts. The microcontroller can ignore a device request. It can also ignore the device request just by masking the bit or masking the interrupt enable bit of that particular peripheral device or interrupt device. Now what is an interrupt service routine? As I told you that a set of instructions when executed providing the service to the interrupted device. So it is a program which is related to an interrupted device. So whenever the processor executes this particular program, it means that the processor has provided its service to the interrupted device. So for every interrupt, there is a fixed location in memory that holds the address of its ISR. So here, as processor can handle multiple interrupts. Now all these ISRs are placed inside the or stored inside the memory, and the processor will not know the starting address of each and every ISR. Okay, now all these addresses are placed inside one memory location, and that location is called as interrupt vector table. Now let us see what is that interrupt vector table, how it looks like. So here, as you can see, this is the interrupt vector table, where as 8051 is having totally six interrupts, it can provide its service to 6 interrupts. So here you can see reset is the interrupt vector which is provided at the location 0000. Okay, and it is generated with the help of the pin 9. And external hardware interrupt, and whose ISR memory location is from 0003, and it is generated by using P3.2, that is port 3's second pin. And timer 0 interrupt, which is TF0, and the ISR location is 000B, and external hardware interrupt 1, and here the ISR location is 0013B, sorry 0013, and it is generated by using P3.3. And timer 1 interrupt, that is TF1, serial communication interrupt, it can be generated either by RI or else by TI, and the memory location for this that is ISR memory location is 0023. Now steps in executing an 8051 interrupt. Now what happens if an interrupt is generated? Assuming that the processor is doing a task, now one interrupt is generated. Now what happens? Okay, how the processor is going to respond to that particular interrupt? It finishes the execution, it is executing and saves the address of the next instruction onto the stack. So it means whatever the instruction which is presently it is executing, that gets executed completely, and then it will place or it will store the value which is present in the program counter onto the stack. As we know that program counter is a register which would be holding the address of the next instruction. Okay, so this value will be loaded onto the stack or else pushed onto the stack. It also saves the current status of all the registers. So whatever the registers that are involved in the current execution, now all those register status would be pushed onto the stack. It jumps to a fixed location in memory called the interrupt vector table. Now after pushing the status of each and every register onto the stack, then it jumps to a location in the memory, and that location is called as interrupt vector table. Now from the interrupt vector table, it gets the address of the ISR and jumps to that particular location. The microcontroller starts to execute the ISR until it reaches the last instruction of the subroutine, which is RETI. Now after jumping to the location, it starts executing the ISR, and it will execute until RETI is reached. Okay, now upon executing the RETI instruction, which is nothing but return interrupt, okay, return from the interrupt, RETI instruction, the microcontroller returns to the place where it was interrupted. So as soon as it executes RETI instruction, then the control will be transferred from the ISR to the main program from where it has to be resumed. Okay, so first it gets the program counter address from the stack by popping the top 2 bytes of the stack into the PC. Then it starts to execute from that address. So this is what happens. It will get the program counter address and then starts executing from that particular address. As we know that now program counter is holding the next instruction, okay, which is already stored onto the stack. So there are totally 6 interrupts in 8051 reset, and 2 interrupts for timers TF0 and TF1, 2 interrupts for hardware that is INT0 and INT1, and then 1 interrupt that is either TI or RI, which comes under serial communication interrupt. There is a limited number of bytes for each interrupt, as we know that as just now we have seen the interrupt vector table where a limited number of bytes are associated for the ISRs of each and every interrupt. For the reset interrupt, it is only 3 bytes are provided, and for all the other interrupts 8 bytes are provided. Okay, if ISR is too short for if ISR location or ISR memory is too short for storing the program which is related to the interrupted device, then we have to use ljump instruction so that the control would be transferred to a location where actually the ISR is stored. Programmers must enable these interrupts before using them. So we have to enable the interrupts before we want to use them. Now for enabling the interrupt, we have to access one register, and that register is interrupt enable register, and it is a 8-bit register as you can see, and it is a bit addressable register. It means we can individually access each and every bit without affecting the other bits. Okay, now EA is a global enable bit. If we want to use any kind of interrupt, if we want to enable any kind of interrupt, then this particular bit should be programmed to 1, and later on we have to program any of these bits for enabling the respective interrupt. Okay, so EA should be 1, and then if I want to enable serial communication interrupt, then this particular bit should be programmed to 1. If EA is 0, then even if we program any of these bits, will not enable the interrupt. Let us see here, EA equals 0, so no interrupt is acknowledged. If EA is 1, each interrupt source is individually enabled or disabled by setting or clearing its enable bit. Okay, so this should be always 1 for generating any kind of interrupt. Okay, after making it to 1, then we have to program any one of these bits to 1 to select or to enable any one of these interrupts. Okay, so this is RATI interrupt, and this is TF1 interrupt, EX1 is INT1 interrupt, ET0 is TF0 interrupt, EX0 is INT0 interrupt, and ET2 is used in case of 8952 controller. Okay, now let us see the steps for enabling the interrupt. To enable an interrupt, we take the following steps. EA should be 1, so that we can enable all the interrupts are enabled. If EA is 0, no interrupt will be responded to, even if the associated bit in the high is high. So even if any of the interrupt bit is high, if EA is 0, then it will not recognize those interrupts. Okay, enable each interrupt by setting its corresponding bit in IE. So we have to we can enable any interrupt by programming a particular bit in IE register. Let us see an example. Here, enable the serial interrupt, timer 0 interrupt, and external hardware interrupt. Disable the timer 0 interrupt. So disable or mask is similar. Show how to disable all the interrupts with a clear or with a single instruction. Okay, so initially we'll enable serial interrupt, timer 0 interrupt, and then clear, and then external hardware interrupt 1. Okay, as you can see here, initially EA should be programmed to 1 in order to enable any kind of interrupt, and then serial interrupt should be 1, INT1 should be 1, and then timer 0 should be 1. Okay, so now this particular function is made with the help of move instruction, or else I can also access individual bits. Why? Because this IE register is a bit addressable register, therefore individual bits can be or else performing some operation on individual bits is done with the help of set instruction, set B instruction. As you can see, set B IE.7, which sets this particular bit to logic 1, and set B IE.4, which sets serial interrupt, and set B IE.1, which sets hardware interrupt 1, set B IE.2, which sets enable timer 0. Now let us see how to disable all the interrupts with a single instruction. Since IE is a bit addressable register, we can use the following instructions to access individual bits of the register. So I am masking some of the interrupts, that is clear IE.1, which is going to mask timer 0 interrupt only, and clear IE.7, this is going to disable all the interrupts. Okay, now let us see how to program the timer interrupts. So in polling, we have to wait until the TF is raised. So this is what the instruction which we have to use, which indicates we are using polling method. Using interrupt, whenever TF is raised, the microcontroller is interrupted and jumps to the interrupt vector table to service the ISR. As we know that the controller is going to perform its operation until it gets an interrupt from the device. So here, in case of timers, whenever a rollback condition occurs, then the TF flag will become 1, will generate an interrupt. Therefore, the processor is going to stop the present execution and then responds to the ISR of the timer interrupt. Okay, and these timer interrupts are stored in 000B location and 001B location, that is ISRs of the timer 0 and timer 1. Now let us see an example. Write a program that continuously gets 8 bits data from port 0 and sends it to port 1, where port 0 is acting as input and port 1 is acting as output, while simultaneously creating a square wave of 200 microseconds period on pin 2.1. Use timer 0 to create the square wave. Assume that crystal is 11.059 megahertz. So whenever an interrupt is generated, or whenever the timer 0 generates an interrupt, then it has to create a 200 microseconds waveform on P2.1. Okay, let us calculate the time period initially. So TH0 equals 100 microsecond. I'm just calculating for half clock cycle. Okay, therefore 1.85 microseconds for one increment, the time required for the timer to get incremented by 1, therefore I'll get 92 for half clock. Okay, so here this value should be loaded into TH, so that I'll get 100 microseconds and 100 microseconds. Let us see the program. So initially I'm writing ljump main, okay, which is going to bypass the interrupt vector table. Therefore now the control passes to the main program, okay, and it executes the main program. Now here I'm making tmod to 02. I'm initializing tmod to 02, which means I'm using timer 0 in mode 2, which is nothing but auto reload, and then move p0 comma 0ff. I'm loading or initializing p0 with ff, and then th0 is now initialized with a4, okay, and I'm enabling, that is EA should be programmed with 1, and then timer 0 interrupt should be programmed with 1, and then I'm just running the timer by using this setB instruction. Now I'm sending the value which is present in P0 into the A register, and I'm just copying the value which is present in A into P1 register, and then I'm doing this operation continuously. Why? Because short jump back. So again the control passes to this back label and then executes the same instructions. Now this operation is continued until TH0 until TL0 TL0 is loaded with FF. So as soon as TL0 is loaded with FF, then it generates an interrupt, so that this ISR gets executed. Now in this ISR I'm writing CPL, which is nothing but complement P2.1. so for the generation of interrupt, whenever the interrupt is generated, then this P2.1 gets complemented. In the ISR for timer 0, notice that there is no need for CLR TF0. Why? Because the ISR is going to, or the 8051 clears the TF0 or TF1 flag internally upon jumping to the interrupt vector table. Now let us see how to program the external hardware interrupts, which is INT0 bar and then INT1 bar. Now 8051 has two external hardware interrupts, as we know, that EX0 and EX1, and whose pins are INT0 and then INT1. These two pins are used in timer counter. INT is a trigger for hardware control, as we know that if gate bit is 1, then we have to generate an interrupt for starting or stopping the timer, and they are enabled and disabled using IE register, as just now we have seen that. Upon activation of these pins, the 8051 gets interrupted and jumps to the vector table to perform the ISR. So if these pins are activated, then the processor will be stopping the present execution and then jumps to the ISR to provide the service to the interrupted device. There are two activation levels for the external hardware interrupts. Now the processor is going to understand or processor is going to recognize only two levels present on these particular pins, that is low level triggered and falling edge triggered. Why? Because those two pins are active low pins. This is chosen by IT0 or IT1 in TCON register. On reset, IT0 and IT1 are both low, making external interrupts low level triggered. Okay, so IT0 and IT1 are the two pin or the two bits which are present inside this TCON. They are going to select the type of trigger that we need. Okay, if these bits are programmed to 0, then it means we are going with low level triggering, and if these bits are programmed to 1, then it means we are going with falling edge triggering. Okay, and IT here is nothing but interrupt type. As you can see here, these are the two external hardware interrupt pins through which we can generate the external hardware interrupts. Now let us see something about low level triggered interrupt, also called as level activated interrupt. After the hardware interrupts in the IE register are enabled, the controller keeps sampling the INT pin for a low level signal once each machine cycle. So the processor is going to sample this INT pin for every machine cycle as soon as we enable this IE register. So INT0 and INT1 pins are normally high. So initially they are high. Why? Because they are active low pins, but whenever a logic low level is applied to them, then it triggers the interrupt. Okay, and this logic low level should be maintained for 4 machine cycles so that the processor can recognize that particular interrupt. The duration of the low level triggered interrupt, the pin must be held in a low state until the start of the execution of ISR. If the INT pin is brought back to a logic high before the start of execution of ISR, there will be no interrupt. So we have to make logic 0 on that particular pin for a duration of 4 machine cycles. If it is logic high before 4 machine cycles or before the start of ISR, then it will not recognize the interrupt. It will not provide the service to the interrupt. The low level signal at the INT pin must be removed before the execution of RETI. Otherwise, another interrupt will be generated after one instruction is executed. So we have to remove that low level signal on INT pin when it is executing RETI. Why? Because if not, the other interrupt will be generated. That means the same interrupt generated for the next time. Falling edge triggered interrupt. After the hardware interrupts in the IE register are enabled, the controller keeps sampling, as just now I said. When a high to low signal is applied to INT 0 or INT 1 pin, the controller will be interrupted and forced to jump to the ISR location. So if there is any high to low signal on this particular pin is applied, then the controller jumps to the ISR. Okay, falling edge. The external source must be held high for at least one machine cycle and then held low for at least one machine cycle. So we have to maintain this particular duration for the high pulse and as well as for the low pulse. Then only the processor can recognize this kind of interrupt. And here the IE0 and IE1 of TCON register goes high whenever a falling edge is detected. So here IE0 and IE1, these are the two bits which are present inside TCON register. They are going to represent the status of the falling edge interrupts. Okay, the IE0 and IE1 function as interrupt in service flags. When any of these bits is 1, it indicates to the external world that the interrupt is begin serviced now, and on this INT pin no new interrupt will be responded to until the service is finished. So here if these bits are 1, then the other peripherals know that then they cannot generate any kind of interrupt until this particular interrupt is executed or interrupt is serviced. The RETI clears IE0 flag. During the time that the ISR is being executed, the INT pin is ignored no matter how many times it makes high to low transition. Okay. Now let us see those bits, that is IE, IT bits in this TCON register, and these are related to the interrupt bits. Okay. Now here IT 0 for external interrupt 0, IT 1 for external interrupt 1. Now if this particular bit is set by software for specifying falling edge or low level triggered. If it is 0, it means low level triggering. If it is 1, then it means you are going with falling edge. Now IE, these are the bits which are used for representing the status of the falling edge interrupts. Now let us see one example. Assume that INT 1 pin is connected to a switch that is normally high. Whenever it goes low, it should turn on an LED. The LED is connected to P1.3 and is normally off. When it is turned on, it should stay on for a fraction of a second. As long as the switch is pressed low, the LED should stay on. So here we have to connect one switch to the INT and it is normally high. Whenever this switch is pressed, then it would be connected to logic ground. Okay, that means it will be receiving a 0. It means we have generated an interrupt. Now whenever this interrupt is generated, we have to turn on an LED which is present or which is connected to P1.3, and it should stay on for a second, and we have to make this particular LED to be on until this particular switch is pressed. Okay, let us see how to do that. So as I told you, we have to bypass the interrupt vector tables. So for that we have to use ljump main. So now the main program gets executed. Now here I am enabling all the interrupts, and one particular interrupt is enabled, that is INT 1, and then sjump here. So I am executing this instruction until I get an interrupt. As soon as that particular interrupt pin is turned on, okay, as soon as that particular interrupt pin is turned on, then or interrupt is generated, then ISR gets executed, which is present in 0013 location. So initially we are setting P1.3, which is nothing but the LED which is connected to P1.3 will be turned on, and then R3 is loaded with 255 value. Why? Because we have to generate 1 second delay, and then P1.3 is cleared, and as soon as this processor executes this RETI instruction, then the control will be moving to this particular instruction. Now let us see how to program the serial communication interrupts. There are two serial interrupts in case of serial communication, RI and TI. In the 8051, this is only one interrupt set aside for serial communication. This interrupt is used for both send and receive data. Okay, while we are sending some data, if a character is transmitted, TI would become 1, generating an interrupt. If one character is received, then RI would become 1, indicating that one character is received, and it will also generate an interrupt. If the interrupt bit IE.4 is enabled, when RI or TI is raised, the 8051 jumps to memory to execute the ISR. Okay, so here if this particular bit is enabled, and if RI or TI is set to logic 1, then the 8051 or the controller executes this the ISR, which is located at 0023H location. The last instruction before RETI is clearing of the RI or TI flags. This actually we have to clear this RI and TI flags at the end of the ISR, because processor doesn't know actually which particular bit have generated the interrupt, whether TI or RI. But in case of timers, TF is cleared automatically at the end of the ISR. And let us see how to assign the priorities in case of 8051. When the 8051 is powered up, now all the priorities are shown here. That is, external interrupt 0 will be having highest priority, and timer interrupt 0 will be having the second highest priority, and external 1 interrupt will be having third highest priority, and timer 1 interrupt will be having fourth highest priority, and the last, that is low priority, is for RI and TI. Okay, if you want to assign a user defined interrupt, now that is done with the help of IP register. We have to access IP register, and here let us go with an example, discuss what happens if interrupts INT0, TF0 and INT1 are activated at the same time. Assume priority levels were set by the power-ups reset and the external hardware interrupts are edge triggered. So assuming that if these three interrupts are generated at the same time, then what happens? If these three interrupts are activated at the same time, they are latched and kept internally. Then the 8051 checks all 5 interrupts according to the sequence listed below. Okay, so if all these interrupts are generated at the same time, then it is going to receive all those interrupts, but it will provide the service to the interrupt which is having highest priority. As you can see that INT0 is having highest priority, so it is serviced first, and then TF0 and then INT1. So setting interrupt priority, that is user defined or user defined priority levels to the interrupts. To give a higher priority to any one of the interrupts, we make the corresponding bit in the IP register to high. Okay, upon power up reset, IP contains all zeros, making priority sequence based on IP bit equals to 1. First, high priority and low priority, 2 levels. Second, if some interrupts have the same priority than others, they are serviced according to the sequence table. So this is the register which we are talking about, and external 0 priority bit, timer 0 priority bit, external 1 priority bit, timer 1 priority bit, and then serial communication priority bit. If any of these particular bits are programmed to 1, then the respective interrupt will be provided highest priority. Interrupt inside an interrupt. Assuming that the processor is executing an ISR, and during that time, if one more interrupt has generated, now the processor is going to recognize that interrupt if it is a high priority interrupt. If it is a low priority interrupt, then it is going to execute the ISR. It is going to continue the execution of the ISR which it is doing, and after completion of that ISR, it responds to the next interrupted device. Triggering the interrupt by software. So we can also generate the same interrupt with the help of software, that is by using this instruction, that is set B, and programming this TF1 or TF0 to 1, which will generate a software interrupt. Thank you.